lecture, I would like to come back to this representation connected with the shape of the nuclei. So if you remember, by Marc Caprio said that if you have the gamma degree of freedom, only 60 degrees are important, because then you have a repetition along other axes of the same shape. So one represents this here by the length of beta, so in this direction, length of beta, and then here the value of the angle gamma. 0 degree is prolate, 60 degrees is oblate. Now, what is plotted here are, you make a mesh of points, and for every value of beta and gamma, you calculate the energy of the ground state in this coherent state formalism. And what is plotted here are equipotential surfaces. You cannot read it, but it's saying minus 1500 here, and here minus 1000. And so there's about 100 between each surfaces. And if you do that, then you can find out where the minimum is. So what is then the deformation of a given Hamiltonian as a function of its parameters? So one way you can apply it is by fitting parameters to actual nuclei, and then making this plot, and then you find out, well, it has one minimum, for instance, here at a prolate deformation. In these plots, you only vary beta because gamma is not important. Gamma in U5, because you're at beta equals 0, has no influence. And in SO6, you have this gamma unstable. So it means that the potential energy surface in gamma is completely flat. Now, one consequences of dynamical symmetry is that it leads to selection rules, and that's a very important property. So you get very stringent selection rules if you have a dynamical symmetry, because these selection rules allow you, of course, to test experimentally whether the dynamical symmetry exists, whether the quantum numbers are right and are fulfilled in nature. Now I want to illustrate this selection rule with one example, and the example is 196 platinum and the E2 quadrupole, electric quadrupole transition properties. Now recall from the introduction that if a generator of a Lie algebra or a subalgebra, we always have this commutation rule defining the set of generators of a given Lie algebra. And so they commute, and then we found out that the energy is a function of a quantum number alpha, but we can make, if we apply now such kind of generator acting on one wave function, then we can construct degenerate wave functions having the same energy. And this quantum number, because it holds for all quantum numbers, for all generators, if I have a generator and I act now on this state, I cannot change the quantum number alpha. Yeah? So the generator cannot act outside the irreducible representation in this case. So this is very important because this leads to selection rules. So it cannot connect states having a different quantum number with respect to G. Now, if you have E2 transitions, you don't want to change the number of bosons. Yeah? So it means your operator has to be a combination of a creation and an annihilation operator, because otherwise you end up in another nucleus. But creation and annihilation operators are generators that we have seen. They are generators of U6, and certain combinations of generators are generators, for instance, of the SO6 algebra. Now, it turns out that the transition operator in the O6 limit is a generator of SO6. So it's an operator which is just S decker D plus D decker S. Now this has consequences, because that means that it's an SO6 scalar, so it cannot act outside the SO6 representation. And we can write down the tensorial character of this operator. It's, of course, 0. Then it's 0, that's the SO6 scalar property. Then, of course, it's 1 for SO5, and it's a quadruple operator. Now, the consequence of this is that if E2 transitions between different SO6 representations are absolutely forbidden as long as we have a good SO6 dynamical symmetry. Now, this is platinum 195, and what is given here on top are the SO6 quantum numbers. So these states all have SO6 quantum number 6. These have SO6 quantum number 4, and these have SO6 quantum number 2. So it means that if the SO6 symmetry is a good one, E2 transitions from this 2 plus state to the ground state are absolutely forbidden, or to any of the other states are absolutely forbidden. So that's a clear prediction. Yes?
What is the maybe physical or intuitive picture of what the SO6 quantum number represents?
It's not so easy. For SO5 you have this seniority concept. For SO6 you don't really have such a concept, except maybe Pete knows.
It's also seniority, yeah? But then it's a combined
Of S and D, yeah. So it's kind of generalized seniority. Yeah. Now, maybe just to mention, the lowest state have the maximal quantum number for SO6, which is called sigma max often, and it's equal to the number of bosons. So then the next, I have the number of bosons minus 2, and then so on. That's the reduction rules from U6 to SO6. Now, the Rick, in fact, and Jolly Czyzewski have used additional selection rules on the O5 level in order to identify platinum 196 as a good O6 quantum. So you use here now this O6 tensorial character in order to associate the states to these different quantum numbers. But there has not been a test for many years of this E2 selection rule between states having different sigma quantum numbers. Recently, the group of Norbert Pietrala and my group have now completed a test and come to the same result, which unfortunately I have not included in this talk. But about many years ago, 14 years ago, I took 24 years ago. Man, we are getting old.
You were young then.
Yeah, I was young. Together with Rick.
I was old.
Yeah, he was already old. Yeah. We did an experiment using a special technique, which is called the gamma ray induced Doppler Brooding method, and we determined the lifetime of these states, or we could not really determine the lifetime. We determined an upper limit of the lifetime of these states. And now you have to see that these states, they belong to the higher or the lower O6 quantum numbers, and so the transitions to all these states are absolutely forbidden. And only the transition E2 from this state to this state is allowed. And so we have here also a theoretical prediction that this is allowed, or from the fifth 2 plus to the fourth is allowed. And the other ones are all strictly forbidden. And so we could determine experimentally that we have an upper limit which is very small for all these states. And recently we determined a lower limit. And so we could show that, okay, they are not exactly 0, but they are almost compatible with 0. So it means that we could test these quantum numbers to be trustable in platinum. There is another selection rule concerning O5, and there it turns out that this selection rule causes a problem because it says that all quadrupole moments should be equal to 0 because of this O5 selection rule, which says the value of the O5 quantum number should change with 1. And of course, if you have the same state, then the value is not changing. And so, because of the O5, all quadrupole moments are forbidden. And this is experimentally not really the case, because experimentally we will come to that a little bit later. The quadrupole moment is non-zero, but it's still small for a quadrupole moment. Okay. Now I come to the next subject, which is partial dynamical symmetries. Now, dynamical symmetries, as we saw them, they lead to solvability of the complete spectrum. Existence of exact quantum number for the complete spectrum, and predetermined structure of the wave functions independent of the used parameters. That's what the dynamical symmetry causes. Of course, nature is not always very generous, and nature does not always fulfill the strict conditions of a dynamical symmetry. And so we can now relax on these conditions and construct Hamiltonians such that only some states keep all the quantum numbers, that all eigenstates keep some of the quantum numbers is another possibility, and finally, if we combine both, that some eigenstates keep some of the quantum numbers. Systems exhibiting one of these three conditions have a called partial dynamical symmetry. And so we will see that with the example of some concrete examples. First case. Consider that I mix the U5 dynamical symmetry. U5 is U5 plus SO5 plus SO3, and the SO6 dynamical symmetry. SO6 was SO6, SO5, and SO3. So if we mix now, I have here a kind of tuning parameter alpha, which I can switch on and then switch off the U5 term and switch on the SO6 term. Generally, these have not a dynamical symmetry, and the complete spectrum cannot be solved analytically. However, because both groups have SO5 as a subgroup, followed by SO3, the quantum numbers tau and L and M are conserved all over this transition. The analytic expressions are not conserved, but the quantum numbers are conserved. So it's a symmetry in which all eigenstates keep some quantum numbers. As an example, here you see the spectrum. Alpha being 0, you have the U5 spectrum with here the two phonon states, 0, 2, 4. And if you now switch on alpha and alpha becomes 1, you have the SO6 spectrum where you have a different sequence of states. And especially this 0 plus of the two phonon which was discussed, it's going up and it forms the lowest state of this other sigma max minus 2 O6 quantum number. However, in the whole transition, the seniority of this state is 1, and it stays 1 over the whole transition, becomes here seniority 1. This is seniority 2, coming from here, seniority 2, and the seniority quantum number is held all over the transition. So, next week there will be the 15 Capture Gamma Ray conference, and so this is the cover of the 1993 Capture Gamma conference, and what you see here is the wave functions plotted in a U5 basis for the states. You see this kind of peaked structure, and many elements are 0, yeah, overlap, and this is a consequence of this conservation of the seniority quantum number. So you can see that more clearly if you now compare it, if you do this expansion in an SU3 basis, so any basis can be used to make a numerical calculation. You have this many small components, but if you are in between, then you get this conservation of the O5 quantum numbers. Now an example of case 1 we will construct is partial dynamical symmetry within the SO6 limit. So this is again platinum 196. These are the sigma max states with n equal 6, then sigma equal 4, and then sigma equal 2, which we discussed before. And this is the theoretical spectrum. If you look for the sigma max state, the description is rather good, but here there are some deviations in these higher states. So the question is, can we now construct a Hamiltonian which keeps the symmetry for these states but changes the energies and the wave functions or mixes them for the higher lying states in order to get a better description?
So before
Yeah.
we go to the next slide, I was wondering if the angular momentum of these states can be measured.
Yeah.
Can the sigma be measured, or is this something we just prescribe by the model?
We can measure it by using the selection rules, more or less. And also, maybe I didn't mention that, we have analytic expressions, we have analytic wave functions, yeah? And then we have the operator, and so we can now calculate transition BE2 values as a function of the quantum numbers. And so these formulas we can now test. So in this sense we can test other quantum numbers, yeah, like we test angular momentum.
It's not directly measured,
No,
but it's deduced.
it's tested, yeah, deduced, yeah. Now, how can we do that? The first step is we need to construct operators which have a definite tensorial character under the SO6 limit. And so I have here the example. How can we do that? We just calculate analytically the wave functions in the SO6 limit for two S and D bosons. Yeah? So n is 2, and then I can have sigma equal to 2 or 0. And then I can have seniority equal to 2, 1, or 0, and the L value is equal to 4, 2, 2, 0, 0. Now, this is just using the analytic expressions for the symmetries. And then, of course, we have the wave functions also analytically, and these are these combinations. Yeah? This is, again, this vector product. This is 2, 2 coupled to 4, 2, 2 coupled to 2, and so on. Now, the interesting guy is the last one, because this guy has n equal 2, but it has sigma equals 0, v seniority equals 0, and L equals 0. So it's a scalar under O6, O5, and O3. The expression is given here. It's minus a term, a square root, S decker, coupled to 0, and then plus square root 5 divided by 12, d decker coupled to 0. Now, this we can use now to construct a partial dynamical symmetry. How? We choose an interaction such that the interaction working on states with a given sigma always yields 0. And this interaction, we use this two-particle wave function with sigma equals 0. Yeah? So that's, again, this operator is this expression. And then the other one is the same with annihilation operators. So this interaction has then this tensorial character. Yeah? And if you work it out, you can write it in terms of this, what is called a boson pairing operator. Now the important thing is, if I work on a state with maximal value of O6 quantum number, so n bosons, and it's n, sigma is equal to n, then I end up with the annihilation operator in a nucleus with n minus 2 bosons. And then the maximal value of sigma is n minus 2. And there is no state with a value n by this annihilation. And this is now a scalar operator. So the irreducible representation null times n can only yield in the vector coupling at an abstract level n. But n is not present. So it means that if I work with this interaction on this maximal O6 quantum states, it will always yield 0. So it has no effect. However, if I use now this interaction and I work on a state with lower sigma quantum numbers, like n minus 2, null times n minus 2 is n minus 2, but I will end up in an atomic nucleus with n minus 2 bosons by this annihilation. There, these states are present. So it means that this interaction will only act on states having not the maximal value of the SO6 quantum number.
So what does this top line mean then again?
We choose an interaction which is such that for certain states, the interaction yields 0. Now, I do it here explicitly only with the annihilation, yeah? But of course I have to return in the same nucleus, yeah? And that's why I need to have a creation and an annihilation operator. But the annihilation already yields 0 for these sigma max states. So if I then multiply it with the creation, 0 times something is 0. Okay. Now, I'm sorry. So this is the way one can construct partial dynamical symmetries, and in fact you will do it in the SU3 limit in the afternoon. You will also construct a partial dynamical symmetry and program it yourself. So if we have the Hamiltonian SO6, SO5 and SO3, that is a normal O6 Hamiltonian, I can now add this interaction here, P plus P minus, with a parameter. If I have the parameter equal to 0, I get just the original O6 spectrum, which I can compare with platinum. And if I now vary the parameter, you see all these sigma max states, they don't change anything. Their energy is not changing. On the other hand, these states are changing their energies, because these are coming closer compared to here, and closer to experiment, and also here they are coming closer. And so that's an improvement of this O6 by using the concept of a partial dynamical symmetry. I want to conclude with some practical things. How to determine the tensorial character of an operator. Yeah? In order to find out selection rules, one needs to have this good definition of the tensorial character of the operator, because otherwise I cannot use this extended Wigner-Eckhart theorem. Now, there are some tricks how to do it. Let's take a transfer operator. Yeah? So we go from one nucleus in another even nucleus by a transfer reaction, for instance, PT transfer, and that of course corresponds in the model by creating an S or a D boson state. Yeah? So two particle transfer reaction. And now how to determine the transfer operator's properties? It's very easy. You just take the reduction rules in the O6 chain, and I give them here. So sigma is the number of bosons, minus 2 and so on. Tau is given as a function of sigma, and L is given as a function of tau here. With the missing label, it's a bit more complicated. But you have these reduction rules in textbooks, and so you now have a very easy task. You just take one boson, so then sigma is equal to 1, tau is equal to 1 and 0, and L is then corresponding equal to 2 for the d boson and 0 for the s boson. So we have here the tensorial character of these transfer operators in the simplest form, immediately derived by using the expressions for the wave functions or the reduction rules. Second example, which we discussed before, is again the example with this partial dynamic asymmetry. We just look at the wave functions for two boson system, and then we select those which having sigma 0, 0, 0, and then this is the expression of the wave function from the textbook, and so we can now have this operator by just taking this combination, and we can rewrite it as a scalar product and things like that. So this is the same trick. In fact, we just put in small values of the bosons and do the reduction rules. So with this, I would like to end my first lecture. Yeah? Yeah.
You define the P plus, but what is P minus?
P minus is the annihilation operators. So I use this table because this is as a function of the creation operators, but you just change the creation in annihilation, and then you have the P minus. Because you have to end up in the same nucleus again. So if I remove two bosons, then I have to add again two bosons. But in the removal of the two bosons, already this partial dynamic asymmetry takes place. Yeah. Okay, now this was the end of lecture 1. So now I have to just change to lecture 2, which apparently is not so easy. Yeah, okay. Yeah, it's okay, Pete. Yeah. Now, the lectures will be available on the website also. I hope this will disappear. Now I will come to another subject which is associated with the shape of a nucleus. Yeah? So we will discuss now shape phases and critical point solutions, which will be discussed also in detail tomorrow by Norbert Pietrala. Now, most nuclei are very well described by an extremely simple IBM Hamiltonian due to this guy. It's your fault, yeah. Now, it's called the consistent Q formalism, and it has two terms. It has the Casimir operator ND, it's the first order Casimir operator of U5, and the quadrupole operator as a function of this parameter chi. Remember, this was the sixth parameter we had as a scalar product with itself. We have...
John, I have to interrupt.
Yeah.
You got to give Dave Warner credit.
And Dave Warner, yeah. You have a structural parameters, eta, here, which is again of the type that I switch off the ND term and switch on the QQ term by varying eta. I need some normalization by the number of bosons because this is a quadratic term and this is a linear term. And I have a scaling factor, so I can expand. The structure of the spectrum is given by eta and chi, and this is just an adaptation, a scaling factor expanding the spectrum in order to compare with actual nuclei. So two structural parameters, eta and chi, and a scaling factor. Now the first term generates spherical shapes. Yeah, these are the quadrupole phonon vibrational nuclei, while the second term generates deformed shapes. This is part of the Casimir operator of SU3, and it makes deformed structures. And so we have a kind of Ising Hamiltonian in which we have two competing structures which we can, by a control parameter, switch on and switch off. Now, remember this Kasten triangle? We have now eta in this direction, in fact going eta 1 is u5 here, and chi going like this angle in this direction. Now, the amazing thing is this is a very simple Hamiltonian, but it has 4 dynamical symmetries. So the first one is eta equal 1, then I have the u5 limit of the interacting boson model, and this is situated here in this corner by eta equal 1, and chi has no influence. Then the second dynamical symmetry it has is if we take eta equals 0 and chi equals 0, then I am in the SO6 limit of the interacting boson model. So we define this point here, and so here chi equals 0, we have a SO6 dynamical symmetry. Now if we take eta equals 0 and chi with a special value minus square root 7 divided by 2, then I am in the SU3 limit. So I have the deformed nucleus, prolate deformed nucleus. So this is situated here. And then finally, if eta is equal 0 and chi is plus 7.5, I have this SU3 bar symmetry. So these are defining oblate rotors. And so we see here, with these 2 parameters, we have 1, 2, 3, 4 dynamical symmetries. And the interesting thing is that we can now study how you go over from one of these dynamical symmetry-like nucleus to another one. For that we use now the formalism of the coherent state formalism. So again, this is the energy for n bosons with the parameter eta and chi for different values of beta gamma, and I have this expression. It has a beta square term, it has a beta to the 3rd cosinus 3 gamma term. Remember, that was also something Mark had, and then a beta to the 4th term. Now this term is interesting because beta high 3 cosinus 3 gamma, beta is always a positive value, and so if chi is negative, then cosinus 3 gamma has the minimum at 0 degrees. So these are the prolate shapes. However, if chi is positive, then this term is positive, and then we need to have here minus 1. And so the minimum is then at 60 degrees. Yeah? So this term is defining whether we have a prolate or an oblate shape. Now, shape change in atomic nuclei, it's a little bit complicated compared to solid state physics. Now, how can we observe shape phase transitions in atomic nucleus? We can look at the deformation of the ground state. If we have a spherical nucleus, then we have a spherical deformation or no deformation of the ground state. However, if we have a rotational nucleus, then we will have a prolate or an oblate form for a spheroid for the deformation of the nucleus. Now, we can compare now that to phase transitions in crystals, in this sense that if you have a phase transition in a crystal, you change some external parameters, and then you go over from one particular crystal structure to another one. And this happens in general as a function in solid state physics, as a function of pressure, temperature, or concentration of certain impurities and things like that. Now, in atomic nuclei, this happens as a function of the number of valence nucleons. So if you have a low number of valence nucleons, you generally have a spherical nucleus. If you increase the number of valence nucleons, then you will get a transition to a deformed nucleus. Now, for solid state, this guy, Landau, Lev Landau, you know probably from Landau and Lifshitz, Mir physics books, described this kind of phase transitions in 1937 in a general way. And he started from a thermodynamical potential, thermodynamical potential phi, which also has external parameters like the pressure and the temperature you can vary, and which has an order parameter, psi, which describes the structure. For instance, the crystallographic structure. Now, in order to do that, we have extended this Landau to atomic nuclei, and so instead of having a thermodynamical potential, we have an energy functional, which is given by this coherent state formalism. And so we have now the energy as a function of the number of bosons, eta and chi, and we have two order parameters because we have the description of the deformation is done by these beta and gamma variables, which Mark Caprio introduced already yesterday. So we see there are some equivalence between both, but instead of one order parameter, we have two order parameters, and instead of two external parameters, in principle, we have three with the number of bosons. Now, how does it work with Landau? So consider we have here the temperature axis and the pressure axis. So now what you have to do is you have to minimize this thermodynamical potential as a function of a given P and T. So in this point we have P1 and T1 given, and then we minimize and look for the minimal value for the corresponding order parameter. So you have to imagine in every point, this is with a constant pressure, you have this kind of energy functional or thermodynamical potential, and you look now for the psi value. This is the psi axis, which corresponds to the minimum. And this, of course, will vary as a function of, in this case, different temperature, constant pressure. Now, if you do that, you can observe phase transitions. And how do they come along? So you have different orders of phase transition. The first order phase transition, let's take the case that we vary by constant pressure, we vary the temperature. Now, what you will obtain is that the thermodynamic function at the beginning will have, for instance, this minimum here at psi equals 0. But then if you now decrease the temperature, then there might be a second minimum developing, but being higher in energy and at a finite value of psi not equal to 0. And then at the critical point, or the critical temperature, both minima become degenerate. So they are at the same energy, and if I now lower the temperature further, then suddenly this psi becomes the only minimum further. So this is our order parameter, psi. Now if you plot what is happening as a function of temperature, then you have for high temperatures, the axis is wrong. It should be inverted. Let's assume that this is a higher temperature and this is a lower one. Then as long as you have this minimum, then you have a certain value for psi, and then if you pass the critical temperature, then suddenly you will have a change of the energy of the minimum. And if you now look at your order parameter, which defines where the minimum is, or psi minimum, then you see a sudden jump in the order parameter by a first order phase transition. So it was 0 the whole time. At the critical temperature, suddenly takes a finite value, and then it increases as the minimum moves in that direction. Now, you can have another case, which is a second order phase transition, in which the potential smoothly rolls from the 0 minimum into a higher minimum. Yeah? So there is no really second minimum, but it smoothly moves, so it's the whole time 0, and then suddenly it changes its value. And if you look at the minimum value, then also it is 0, and there is a kink here, and this increases then as the minimum is getting more to higher values of psi. So that's a second order phase transition. Now, what does Landau do in his theory? He assumes the form of the potential as a function of pt and psi to be a constant value, and then a term with psi squared, psi to the third, and psi to the fourth power, and then of course here you have functions which depend on p and t. Remember what we had before? We had as a function of beta squared, beta to the third, cosinus 3 gamma, and beta to the fourth, these energy functional, and in front were coefficients depending on n, eta, and chi. So it's very similar. Now, Landau considers the case, among other cases, in which beta, b, this term, with a cubic term, is non-zero for everywhere. And of course, this term has to be negative, otherwise this will always yield a minimum at plus infinity. So we have Cpt should be bigger than 0, and beta is non-zero. Now, in the case as a function of p and t, we can define now that the function thermodynamic potential should be continuous as a function of p and t everywhere. But if derivative can be discontinuous at a certain value, and if we have, then we have a first order phase transition. And if the second derivative is discontinuous at a certain value, but not the first one, we have a second order phase transition. This is the Ehrenfeld classification of phase transitions. Now, if we first look for the extremum, so where the minimum has to be, by taking the derivative of psi of this function, and if you do that, you get this equation, psi multiplying by 2a, 3b, psi, 4c, psi squared is equal to 0. And so we see already two possible solutions. Psi is equal to 0 is a solution, or the second term is equal to 0. And then it depends, of course, which one is yielding the lower value of the potential, yeah, in order to find the real minimum. Now, in our case, B is not equal to C is bigger than 0 for all P and T, and so we can now work it out. So we have the minimum either at psi equals 0 or at psi equal to this solution of this quadratic equation. Now, first we consider the case that psi is equal to 0. In that case, we need, of course, that A to be a positive term. Otherwise, it would be a maximum and not a minimum. Yeah? The parabola can be like that, or it can be like that. So we find the condition for the minimum psi equal to 0. We have positive values of APT. It might be that some of these values are excluded because we get another minimum, which is lower. This is a necessary condition, but still there may be, that's exactly what I've written down, there may be a deeper minimum at another value of psi. Now, let's go back to our potential. We saw that the phase transitions will happen, for instance, for the first order, when we have two degenerate minima. One at psi equals 0 and one at psi non-equal 0. But if psi is equal 0, and we look at this expression, all these terms yield 0, and so we get the minimum is phi 0. Let's take phi 0 equal to 0 to make it easy. So then we get the potential is equal to 0. Yeah? And now we can impose this condition, so phi, the first term is 0, and then we can put psi squared outside, and we again obtain a quadratic equation, however with different coefficients here, which we can solve. So if the second term becomes equal to 0, then the condition is it happens when b squared is equal to 4ac. Yeah? If this, then the square root in the solution becomes 0, and so I have a real number. So in order to fulfill this condition, we have now b squared is equal to 4ac. Now, if we insert this in our expression for, say, 0, this is the expression we derived before. Now we insert ac is equal to b squared divided by 4. If we insert that inside here, then it turns out there is standing here 8. Yeah? 32 divided by 4 is 8. And so I have 9b squared minus 8b squared is 1b squared. I can take the square root. And so I have now minus 3b plus or minus b divided by 8c. And it turns out that it's the minus sign which yields the minimum. Why doesn't it do? I'm sorry, it's not working.
That happened once before. Use the arrows.
Yeah, but that's the problem. They don't seem to work. Just, is it a battery?
Now there it goes.
Okay, yeah, good. So we have this second minimum happens now at this critical value of the order parameter, which is equal to minus b divided by 2c. So if psi is bigger than 0, then b has to be smaller than 0 because of this minus sign. Remember, this is always positive. And if psi is smaller than 0, then b has to be bigger than 0. And of course, the condition was on a certain value for the a parameter given by this expression that the discriminant becomes equal to 0. And so this condition is given here again. And so we get a total picture of phase transitions I cannot do this. Yeah. Made by Landau, more or less. So as a function of the parameters b and a, so b is in this direction and a is in this direction, we have these three different phases. The one yielding psi equals 0, which is given by this strict line that alpha has to be positive. Alpha is going in this direction. So this is the alpha 0 line. But you see here, this is the real phase transition. This is where the second minimum appears and disappears. So we go also slightly in the positive for phase 2 and 3, which correspond to positive and negative values of beta. And so the phase transitions happen at these lines and this line. And so we will look a little bit more in detail to that. So if you look at the values of psi, so vertical axis is psi, that is parameter minus a, parameter b. Here, everywhere the minimum is psi equal 0, psi equals 0 for the positive values of a. And then suddenly we will have here a jump in the second minimum, which makes here the positive, the negative values of beta, and here the positive values of beta. And also here there is a jump, so a first order phase transition here in this domain, and in this domain, and in this domain. And then in the center, where the three phases come together, you have a second order phase transition where it goes smooth. And so second order, it looks like that. Psi is 0, and then suddenly there's no jump, but then it increases in square root kind of behavior. Ah. So how can we now apply the same to our energy functional? Now, first of all, we have to realize that we have two variables, beta and gamma. Landau had only one variable. But we can now apply a trick. So again, this gamma value is yielding for a negative value of chi, a minimum at 0 degrees, and for a positive value of chi, a minimum at 60 degrees. Now we have to realize that if we have this expansion here, if you do the expansion, you only get quadratic terms. Yeah? Power 2, power 4, power 6, and so on. So the B3 cosinus 3 gamma is the only odd value of beta in this energy function here. And that determines, as I said, with the sign of gamma, the minimum. So we can now use the trick. We absorb this cosinus 3 gamma in beta. Beta normally was a length, was only allowed to have positive values. But if the minimum is yielding the negative sign, then we just absorb it and we say beta is now allowed to have positive values for prolate rotors and negative values for oblate rotors. Yeah? Then we have more or less absorbed one of the control parameters in the sign of beta. And of course, we can now vary n, but we can also fix n. And most calculations are done using different values of n and varying the other parameters. So like that, are there batteries here? Here there are.
With this thing.
Ah.
Put it again.
Okay. Nothing. Okay. So if we use this trick, then we obtain exactly the form at least at lowest order of Landau. No, it's not a battery because this is what. Yeah. So and then we can fix n, and then we have exactly the form to lowest order of Landau. And so we can apply now Landau's theory, and as a result, and our functions of B, A, and C are just a function of the parameters, the control parameters eta, chi, and n, given here. And so the first order phase transition is when A parameter is 0, so we can solve this and we obtain then this expression. For the spherical to deformed phase transition, and for the prolate to oblate, B has to be equal 0, and if B has to be equal 0, we obtain that chi has to be equal 0. Because chi appears here in B. Yeah? So the isolated second order phase transition at crossing of the two lines is then A equal B equals 0, and so you can work it out and you get this analytic expression for the critical value of eta. Yeah?
We are now considering only axial symmetry.
No triaxial. It has been done for triaxial also, but it's much more complicated. In fact, Marc Caprio did it. But then you have the neutron-proton degree of freedom. Okay. And so now we can apply Landau's theory to nuclei. So Landau's theory, we had 3 phases, one with 0 for the control order parameter, one with negative and one with positive. and we have exactly the same. Here the deformation beta is equal to 0, and here beta takes a positive value including prolate rotors, and beta takes a negative value by this absorption trick including oblate rotors. So we see that the Hamiltonian has 1, 2, 3, 4 dynamic asymmetries, and it has 3 different phases: spherical, prolate deformed, oblate deformed. In between we have first order phase transitions, and we have at this crossing point a second order phase transition at what is called the triple point of nuclear deformation, because you have spherical, prolate and oblate coming together there. I realized this was again work with Rick. Okay. Now how can we bloody thing. How can we see that? We can see that in numerical calculations. What I plot here is as a function of chi and eta. So you have to see it, this is the triangle, but I plot the energy of the ground state in absolute value. And so you see in U5 actually is 0. We will calculate also this afternoon. And then it becomes, if you go into the other phases, it becomes negative. And you see, at least you can imagine, this is a calculation for 40 bosons. If you look at from the side, you can imagine that if you go to an infinite number of bosons, the phase transitions become absolutely sharp. Yeah? We have quantum mechanical effects due to the finite number of bosons leading to quantum fluctuations, which makes that these phase transitions are not absolutely sharp. Yeah? Yes?
In the case of water, the point where the three phases coexist
Yeah.
can be achieved, whereas in nuclear matter, does this point can be reached, and if yes, what
there are some candidates. You will see that tomorrow. There is something equivalent in the collective model, and these are called critical point nuclei. And the corresponding point of this point here has a symmetry which is called E5. Unfortunately, as far maybe Rick will say that it's not true, there are not really good candidates of atomic nuclei for an E5 symmetry. I think you proposed barium.
Well, we looked at barium-134
Yeah.
to see if it worked, and it's sort of. So I would agree with your statement.
Yes, okay. On the other hand, here for the spherical to deformed, there is also a collective symmetry called X5, and there are several nuclei which are candidates, but I'm pretty sure that Norbert will speak about that tomorrow. I think one, yeah, he should. Yeah, yeah. Yeah.
Samarium-152,
Yeah.
gadolinium-154 are examples.
Yeah. So, but some osmiums are also kind of candidates. Now, there are examples I will show for this phase transition here, but that I will discuss in a moment. There are, of course, other variables, like the quadrupole moment. If you go from oblate to prolate, the sign of the quadrupole moment changes, of course. And if you're in between prolate and oblate, so in the gamma unstable region, you cross the quadrupole moment equal to 0. Yeah? So here you have a value 0. It's lying here. So the plot is not in a triangle, it's in a square. Important is to show you the effect of the number of bosons. So this is a realistic calculation with 10 bosons. This is an irrealistic calculation with 40 bosons. And so we can go up to calculations with 100 bosons, and even using the O5 symmetry up to 10,000 bosons. And you see the change in the quadrupole moment becomes sharper, much more sharp if you increase the number of bosons. Another sensitive signature is a Be2 from the second 2 plus to the first 2 plus. And so you see this kind of bird. And so at the prolate oblate, this is increasing enormously, peaking, and then it goes down again. And again, if I do the calculations with 10 bosons, or I do it with 40 bosons, it becomes very sharp. Yeah? because there are less quantum fluctuation. Now, so we come to this picture that we have this kind of phase diagram of this very simple Hamiltonian in which we have spherical prolate formed and oblate formed, and then we have the symmetries and the first order and second order phase transitions. Now, as examples for the prolate oblate and spherical prolate phase transition, we first consider nuclei around platinum-196. Remember, platinum-196 was this example of the O6, which is in between prolate and oblate. Here we have well-defined prolate rotors in hafnium, tungsten, osmium, and so on. And then we continue to the oblate side in the mercury. So if we plot this on the triangle, in fact it's the extended Kasten triangle. Did it do something? Just one minute. Yep. So then we are moving from well deformed prolate nuclei over platinum into oblate, small deformed oblate nuclei. Now, so what I plot here, because it's a little bit difficult to do the calculation, is in the lower, it's the calculation, because the boson number is changing in every nucleus, you have another boson number. So I plot here the ratio of the 4 to 2 for 10 and 20 bosons. And so you see you go from 3.3 to 2.1 or 2.0. And you have a rapid change at the spherical to deformed transition. And if you look at the quadrupole moment in the prolate oblate transition, so here was spherical to deformed transition, prolate oblate transition, then also we will go from negative quadrupole moments for prolate up to positive quadrupole moments for oblate. And a very sharp transition through zero at the O6 limit. So if we now look at some data, these are samarium nuclei, and we look for the spherical to deformed. So these calculations are now done with the appropriate n numbers, and so we compare the calculation here and the experimental points, and you see very nicely that you can classify the nuclei around. I think these are samarium isotopes. I don't remember exactly. I think this is Holton's, but well. Anyhow. So, and you see here at samarium 152 this nucleus which is close to the phase transition. If we look at the osmium to mercury, we clearly in the quadrupole moments have here the negative values, experimental points, the calculation. This is platinum 196, which has not a zero value, but you see that the transition is going sharply through zero a little bit before platinum 196. Maybe at platinum 195.735, it doesn't exist, unfortunately. And then we get here the oblate shapes with still non-zero quadrupole moments for some of the mercury isotopes. Okay. So with that, we close this excursion into shape and phase transitions, on which you will hear more tomorrow by Norbert. And we come now to another subject, which are core excitations. Suppose I have a nucleus close to a closed shell, like cadmium. So in cadmium, I have many neutrons. I have many stable isotopes. It's a very nice isotope, 7 stable isotopes, so you can study it very well. And I have below the tin 2 proton holes. Moreover, the stable isotopes are situated near the mid of the neutron shell. Yeah, that's also an important. 114 cadmium is the mid of the neutron shell. Now, because I'm sitting 2 holes below tin, you can imagine that at a certain moment you can have enough energy to move two proton particles above the 50 closed shell. Yeah? So then I have 4 holes and 2 particles. Such states exist and are called intruder states. The reason why this is possible energetically is if you now consider this compared, here you have 2 protons and let's say 4 neutrons. In fact, you have much more. And so the neutron-proton interaction is an acting between 2 protons and 4 neutrons, while there you have 6 protons, 4 holes and 2 particles, and the same number of neutrons. And that makes a stronger quadrupole proton-neutron interaction. And that lowers the needed energy for these intruder states. Now, how can we describe that in the interacting boson model? We do that by having an n plus 2 system. So we have a block matrix with n bosons, an IBM Hamiltonian with n bosons, and we have an IBM Hamiltonian with n plus 2 bosons. And of course, we have to add a shift in energy. We have to move up these intruder states to higher energy because of the needed energy to make this particle Hall excitation. Now, Chris Heide has described microscopically the value of this interaction. So first of all, you need to have actual value of the difference of the particle states in the Hall states. This is about 8 MeV, so it's a huge amount. But then you get energy you win back, especially by the quadrupole proton-neutron interaction, and that makes that in the middle of the shell, the intruder states occur at a relatively low excitation energy of about 1 MeV. And then, of course, I have to mix these 2 configurations, and the mixing Hamiltonian is quite simple because it has to be a scalar. Remember, it has to be a scalar, so L equals 0, L equals 0. And then there are 2 combinations, S-Decker, S-Decker, coupled to 0, and D-Decker, D-Decker, coupled to 0. We will find out that it is more than that in the symmetry properties of this interaction. And so I have now alpha and beta as parameters in order to describe this mixing of the normal and intruder states. Now, first I would like to discuss that new kinds of symmetries are possible, and one is intruder spin or E-spin. So normally we have the IBM, and we describe this as U6 as the standard symmetry, but now we have 2 types of particles. We have particle bosons and we have Hall bosons. Yeah? So we can distinguish them by using a concept analog to isospin. So we associate an E-spin with the projection plus 1/2 for the particle bosons and the projection minus 1/2 for the Hall bosons. Now, if you do the 2 particle to Hall transformation, then you immediately realize that Ez is conserved in a given nucleus. Yeah? So it means that the general Hamiltonian commutes with the Ez operator equal to 0. And it turns out if you impose some more conditions, you can make Hamiltonians which not only commute with the Z projection of E-spin, but also with E squared. And if they do, then E is a good quantum number. So it means that all states have a given value of E and Ez. So that means you have good intruder spin, and you can now make ladder operators which change particles into holes. This plus change a hole in a particle, and the minus change a particle in a hole. And if you now have a Hamiltonian which in addition commutes with this, then you have intruder analog states. And you will describe now different states in different nuclei. So let's take a look at that. So if I start from the tin isotopes, they have 0 particles, 0 holes, yeah, because they are the closed shell. For the protons, I only note here for the protons, yeah, 0 particles, 0 holes. So Ez is equal to 0, and then the first excitation is a 2 particle 2 hole, so this gets +1 and -1. That's also Ez is equal to 0. But this is E equal 1, and so on. Now, the cadmium isotopes, they have 2 holes, and if I now have the intruder, then, okay, this is -1/2, yeah, because I calculate as bosons. And then I have the 2 particle 4 hole. They also have Ez -1/2, but now E takes the value 3/2. And if I impose intruder analog states, then I can compare the intruder states in cadmium to the normal states in rutetium, because rutetium has 6 holes, and E minus will now reduce the 2 particle to hole, and so we have then a 6 hole state, and Ez projection is -3/2. I can go over the shell, tin, and I can look at the intruder states in tellurium. So that are the analog states of the intruder states in cadmium, and I can go up to the 6 particle states in barium, which are analog states of the intruder states in cadmium. So you've learned about isospin, but you will learn tomorrow, maybe in the afternoon, about F-spin, which is also a SU2 algebra. So you can use the tricks of the symmetries in many different ways. Yeah. So what you do here, in fact, is you have a 2-component system, either proton-neutron, that's isospin, particle hole, that's E-spin, and we will see neutron-proton boson is F-spin. That comes tomorrow, or in the afternoon, partially. Of course, the important thing is to check whether this is close to reality. So what I show here are the normal states in rutetium, the intruder states in cadmium-114. They start at an energy of 1.1 MeV. Yeah? So I've subtracted all the normal states, we will show that later, and I look only to the intruder states. And if you compare, it's reasonable. Up to here there are some larger discrepancies coming up. If I now go to the intruder states in tellurium, they appear at 0.958 MeV. It's less good. Yeah, the agreement is here. It was much better. And if I go to the barium nucleus with only particles, then we get maybe a better agreement than in tellurium. Of course, there are some doubts. You see this question, these clammers, how do you call that? Bracket, parentheses. So it's of course not so easy to identify these intruder states higher in the level scheme. So this is close to 2 MeV. But at least for the first excited state, it's reasonable.
So here,
Yeah.
0 plus is the second 0 plus type, right?
No, in fact, it's the third one. I will come to that.
Oh,
Yeah.
okay. So this is just so high energy, so you could allow for this shell jumping.
Yeah, yeah.
And the particles then jump not one by one, but
No, yeah, because of the pairing. There was a pairing term, and so it's one particle hole excitation is higher than the 2 particle.
But here you have chosen just such excitations that are okay with that, because we might also have just a single particle. I mean, is this a full level scheme, or you have just chosen some levels that would...
No, I will come to that. You will see how I did that.
Okay.
How your question is, how do I get this? Yeah?
No, my question is, this is not the full level scheme.
No,
is
this is not a full level scheme. We will come to that.
okay.
Yeah. Now, okay. In fact, it's the next one. So I want to illustrate how we do that by considering a case study, and the case study is 112 cadmium. So, as I said before, the cadmium isotopes are unique in several respects. Protons nearly fill the Z50 thin shell. Neutrons are near mid shell, and in fact there are 8 stable isotopes of cadmium. So this is clearly the mass region where we can learn about nuclear structure. And so one studies we did are fusion evaporation reactions, alpha to N reactions on palladium populating cadmium-112. And this allowed to establish many multiphonon states up to Nd equals 6. This was also a long time ago. So here you see the comparison. This is an anharmonic rotor where the full lines are fitted states. Yeah, so we fitted excitations up to here. The dashed lines are just non-fitted but extrapolated states. These are experimental spins. They are all determined unique using this reaction. These are the experimental determined states using a simple 4-parameter U5 Hamiltonian. And so you see there is a good agreement even up to very high excitations. Of course, here you don't see the 2 plusers, or it's only the high spin values which can be identified. Now, how do we come to the intruder states? It's just after doing this fit, we subtract from the total experimental level scheme all these states. And what you keep then is this spectrum. Experimentally, you observe that those which are not described by this fit form a 0 plus, a 2 plus, a 4 plus, a 2 plus, a 0 plus, a 3 plus, a 4 plus, a 6 plus.
But Jan, in
Yep.
the previous slide, those ones on the right were left out.
Yeah.
Okay.
Yeah. So this is the first fit, and then there are some levels at this energy which are not fitted, and I plot them here. Yeah. The interesting thing is, this looks exactly like an O6 spectrum. Yeah. Remember, in U5 you had 0, 2, 4, and in O6, as Mark told you, the 0 is higher, and so you have 2, 4. Yeah. Gamma unstable. This at 1.1 MeV, more or less. And so now this was done with a dynamical symmetry fit using the U5 with 4 parameters, and now we can fit using 2 parameters in essence, because we don't see higher non-sigma max states. With 2 parameters we can fit this spectrum, and that's what you see here. That's the 2 parameter fit of the intruder configuration. And it's reasonable. Only the 4 plus and the 2 plus are not so well reproduced. The rest is, with 2 parameters is reasonable. So we see that we have a coexistence of normal states having U5 dynamical symmetry and intruder states having O6 dynamical symmetry. And remember what we learned about partial dynamical symmetry. Both groups, both limits, have O5 as a subgroup. Now, O5 is also defined by boson seniority, so this has to do with the number of boson pairs not coupled to 0. If you look at the Hamiltonian, because it has to be a scalar, you don't change anything of bosons non-coupled to 0, because you create a pair coupled to 0 or you annihilate a pair coupled to 0. S, of course, doesn't change. And so immediately it's clear that this is an O5 scalar. So its tensorial character for O5 is 0, like L equals 0 for O3. So that has consequences, because O5 is a good quantum number, as we saw in the partial dynamical symmetry of both limits. So that means that every state has a definite O5 quantum number. And if I have, let's say, O5 quantum number 2, and I interact with this interaction, then I have to do the vector coupling of 2 and 0 in 5 dimensions. But you can imagine 2 times 0 is 2. Yeah? So it means that the mixing can only occur between states having the same O5 quantum number. For instance, the ground state has 0, this state has 0. They can mix, but they are so far from another that they don't mix. The first excited state here can mix with the first excited state here because they both have O5 quantum number 1. However, this state is very close to another 2 plus state, and so you would expect that it will mix much more strongly with this 2 plus state than with this one. O5 quantum number of this state is 2, and here it's 1, so they cannot mix. They stay pure. And then the 0 pluses here, this is a seniority 0, this was also seniority 0, they can very strongly mix, yeah, due to this selection rule. Moreover, there is more to this story, because we can determine the tensorial character for O6. It means, remember we had these O6 wave functions before, and so we can now rewrite it. I don't want to do the details, but using this table, you can rewrite it as the combination of this guy we used before, 2, 0, 0, 0, and 2, 2, 0, 0. Yeah? So again, how to determine the tensorial character, use just the wave functions and plug it in, and then you come to this solution. Now you see that in front of this term, there's a combination of alpha and beta, and in front of this term, there's another combination of alpha and beta. But again, this term, if it acts on an intruder state, it acts on a sigma max state with n minus 2. If you do the annihilation, you cannot change O6 quantum number, and you end up in a nucleus with a different number of bosons. It's the same nucleus in the normal states. They have n bosons and not n plus 2, and because they have n boson, the maximum value of the O6 quantum number is n. And multiplying n plus 2 with 0, I get n plus 2. The states do not exist in this nucleus. So that means we have kind of effect like in the partial dynamical symmetry, and the mixing Hamiltonian, which is effectively mixing state, is this combination of alpha and beta. This came as a surprise. I have to tell that the referee of this letter pointed this out. Right? But it means that instead of having 2 parameters, you have only 1 parameter, because for any alpha you can get this kind of different combinations of alpha beta yielding this constant factor. And numerically you can test that, and it really is true that you have only 1 parameter. Now, just give some examples of experiments. One very important thing you can do with cadmium isotopes, because you have 8 stable isotopes, you can do inelastic neutron scattering, n(n) gamma. And this is very nice because you can vary the energy of the neutron, and the neutron does not feel a Coulomb barrier. Yeah? So even neutrons with energy 0 can enter an atomic nucleus. And so by varying, you can enter in this nucleus, for instance, at 2 MeV, then afterwards at 2.5 MeV, then at 4 MeV, and so on. And so you measure coincidences, and then you know this is only from states below 2 MeV, and then the new states are between 2.5 and 2 MeV, and so on. So it's a very nice and clean method to do complete spectroscopy in atomic nuclei in detail. Moreover, you can measure lifetimes, as shown here, by using kind of DSAM method, so you can determine the lifetimes, you can determine the branching ratios very well, mixing ratios, and so on. And so you can really make a complete spectroscopy of cadmium isotopes. So as an example, let us look at the absolute Be2 values, which were measured for states in cadmium-110. So here it's denoted 1 phonon, 2 phonon, and so for these multiphonon excitations, you have experimental Be2 values, and if you compare them with the harmonic vibrator, then you have only one which is within the error bars, the other ones are off. If you compare it with the U5 limit, which has finite n effects, you get a better agreement. If you compare it with U5 plus O6 model, so it includes also effects of the intruders, which will mix in certain states and not mix in other states, the improvement is becoming better. So within the error bar, you're now getting also this guy and this guy. And finally, you can now also do a complete calculation using protons and neutrons, degree of freedom, IBM2. Then, of course, you have more parameters and you can improve the description even more. One thing one can test, we can look at 110 cadmium in this kind of U5 SO6 picture. So here we have the 3 phonon states and the absolute Be2 values. Here you have the intruder state and the absolute Be2 values. And you can also describe negative parity states if you include F bosons and P bosons. And so generally up to an energy of about 2 MeV, the agreement is quite good. So finally, of course, let us check what about E-spin. So E-spin gives the prediction that, of course, the Be2s have to be the same. And if you look at cadmium, the intruder Be2, and ruthenium, the normal Be2, they are very similar for the different cadmium isotopes. And again, it's not so good if you go over the closed shell to the barium isotopes. There is a large discrepancy. So it seems that the E-spin analog states only hold on one side of tin. Of course, every dream takes an end. And so the NN prime experiments were continued up to higher energies. So what I showed was up to 2.5 MeV. And so they have been continued to 4 MeV and 3.4 MeV neutrons by Paul Garrett. And part of my group years ago, the analysis took about 15 years. And so you can now extend this in cadmium-112 to much higher energies, up to 3 MeV. And look also, he has also measured all these Be2 values. And then you find out that if you go to the low spin, high phonon states, that the agreement is not good anymore in the Be2s. Yeah, so these are the experimental ones, these are the theoretical ones, and you get quite some discrepancies. But in my point of view, this is of course not so surprising because you are so high in energy in an atomic nucleus.
Jan, what
Yes.
do dashed arrows mean in the lower plot?
These are limits. Yeah. And in fact, 2 minutes too early, so we can have questions. This is the end of my second lecture. So, if there are questions.